Hello, everybody. Welcome to chemistry and one of my favorite topics, thermodynamics. We hit on it previously a little bit in the last chapter when we were talking about solutions and specifically heat of solutions. We talked about enthalpy there. Here we're going to expand a little bit on it. Thermodynamics is by far one of my favorite topics in chemistry because it has the second law of thermodynamics, which is the law of entropy, which states that our world is going towards more disorder, and that flies in the face of evolution, which would state that we are getting more ordered over time. Not true. All right, so, anyways, we will talk about heating curves also. But we want to start with the definition of what thermochemistry is. And you can see that it's the branch of science that studies the transfer of energy. Remember, I said heat is energy during chemical reactions or phase changes. We're going to be talking about phase changes here. So you want to um, understand exactly what is going on when we heat up an ice cube. All right, and we'll go through the different forms of that. They'll give us a heat curve of water so we can talk about that. And we'll also be talking about other situations as far as what's known as latent heat. That's when actually things are melting or boiling. And then you have what is known as the book calls it sensible heat. And what they mean by that is that you can measure it with your senses with a thermometer that allows you to take a reading of the temperature change, the delta T. I refer a lot to that as kinetic energy because, as you know, kinetic energy is proportional to our temperature. And I hope that's intuitive because kinetic energy is 1/2 mv squared. So as our air particles, gases, nitrogen and the oxygen in the air, mainly in the air, moving faster, they're producing more collisions against the container. That's what we call pressure. All right, but against the wall, that would be the pressure. But as they are moving faster, it's heating up the room. All right, so let's get to measuring heat and temperature. As you know, I hope I've made it clear with you that temperature and heat are two different things. Heat is energy, temperature is a measurement. So temperature is a measurement of the average kinetic energy of the particular sample that we're talking about. All right, so heat, you learned, is Q is equal to M cat, as I like to refer to it, as M equals Q is equal to M mass times specific heat times our delta T, which is our change in temperature. And reminder that delta T is TF minus TI. So our final temperature minus our initial temperature is with that. So they're different. I usually start this unit off by asking the students, what's heat? And a lot of them will say temperature, and I'll say, yes, that's part of what heat is. Absolutely. Because that's usually the most obvious one. And then from there, they have a hard time discerning what the rest of heat is. So I asked them, okay, would you want me to throw a thimble of boiling water? A thimble is the little thing they use in sewing, all right, or a small little thimble cup, very, very tiny cup. It's in Monopoly too, the thimble, all right. So, would you want me to throw that, a boiling water at you, or a gigantic pot of boiling water at you? Well, most sensible kids that aren't sadists will say that they would prefer to have the thimble. So I said, okay, so what's that mean then? Why? And they said, well, then it's not going to burn me as much. All right, the heat's not going to get to me as much. Well, that makes sense because mass is also involved in our heat here. All right, and the other term we learned was our heat capacity or specific heat. There's a difference between the two. Specific heat is the amount of energy that can be 1 gram of water raised 1 degree Celsius. All right, so it's the energy of 1 gram of water raised 1 degree of Celsius. That's specific heat, whereas heat capacity has no limitations as far as how many grams it is. It's just, this is the heat capacity. All right, and then our delta T, as I explained earlier. So we're going to go into that a little bit more too. All right, so as you can see, it's measured in joules and in kilojoules on one of your worksheets. The last one about heat of solutions, I had you guys convert from joules into kilojoules because when we talk about molar heat of a solution, that is by definition in kilojoules per mole. And the reason we do that per mole is that we can then share our results worldwide with other scientists. Because heat in and of itself can be different because, again, we have a different mass of it. And mass is related to moles, as you know. So in order to get it standardized, we needed to come up with units in which everyone could understand it. If I was talking to a scientist over in Russia or China or wherever, and I wanted to tell them what the molar heat of the solution was or what the enthalpy of the solution was, I would use kilojoules per mole. And they would understand that, and it'd be comparable data then that we could use. All right, so enthalpy, we talked about that, is the H. That's what our H is. It's enthalpy. It's a new term that you have. It's the thermal energy content of a system at a constant pressure. Now, we're going to assume that everything's happening at standard atmospheric pressure, at STP, for whatever substance that we're talking about. So like right now, there's obviously a pressure that's on us, all right, 14.7 psi, 760 millimeters of mercury, 101.3 kilopascals. All right, you just learned all of that in our gas unit. So that is acting us. So a lot of this enthalpy is happening at room temperature and constant pressure. Changes in enthalpy can be measured with a calorimeter, and this is where I usually had you guys do a lab. We'd do what's called the coffee cup calorimeter, and we'd take a coffee cup, a styrofoam cup, and then a thermometer, and then we usually had some ice cubes in there. And maybe for the first time, I would say, okay, now I want us to wait as it changes temperature. But first, get your initial temperature of those ice cubes. All right, so you usually would get something like a degree Celsius. And then I'd have the students wait until it melted. And then it would go up to roughly about 22 degrees Celsius. Would be our final temperature, and our initial temperature was 1 degree Celsius. And then I would ask the students, okay, well, what is the enthalpy, or actually the heat change? In this case, we're talking thermochemistry here. And they would be able to tell me using the Q equation. Q is the mass of the ice cube. Let's just say for ease sake, we have 10 grams. We know the specific heat of water is 1 calorie. And I say calorie because we're going to be using calorie. 1 calorie is equal to 4.18 joules. You're more familiar with that one. And then in our case here, our delta T is TF minus TI, so we'd have 21 degrees. Now this is 1 cal per degrees Celsius, grams. All right, grams, degrees Celsius. 6 in one hand, half a dozen in another. All right, and then we're left with, in this case, it'd be 210 calorie. All right, it's a positive sign, so we know that endothermic, that situation is absorbing heat, which you think about it, ice cubes melting, they're absorbing heat from the atmosphere. That's why they melt. So it makes perfect sense there. But we're going to be talking about the actual changes in enthalpy. And this is usually the enthalpy of a reaction. Which would be your, well, to be more specific, would be your enthalpy of products minus your enthalpy of reactants. All right. So I'm giving you a lot of more extra information because down the line we will be looking at this. All right, so we have enthalpy of phase changes, sensible heat. Again, that's where we're measuring the temperature, the kinetic energy of a substance on a heating curve diagram. And then you have the latent heat, and that's what's actually producing the phase change itself. All right, and I'll show you on the graph that's coming up next. But know that in latent heat, we do not have any temperature change. So you take a look at the graph here, all right, and we are using ice in this case. So we start with some ice at very low temperature, and then it goes up to the 0 degrees. Well, right here is where it starts dissolving. And right here is where it stops dissolving. That's our latent heat. Notice the temperature. It's at 0. All right, so it's not changing. The same when you get to the 100 mark. This is when it starts to boil. This is when it's done boiling. And then from there, it's heating up that gas, which is steam, very hot gas, or vapor in this case, since it's water. But you can see what the BJU book calls sensible heat is when you have the actual temperature change. So now we have a actual temperature change, or our kinetic energy is changing because it's done its job. It's again, remember when I talked about states of matter and things were close to each other. All right. Well, what's going on here is that you have things as a rock solid, as this -20 ice cube would be, is they're very close and ordered to each other. There's some vibration still going on, all right, but there's not translational energy. There's not rotational energy of the molecules. They're not moving around as such. So you just have your vibrational energy. And then over time, as it does gain that heat and gets to 0, well, we're starting to melt at 0 degrees Celsius. And it will then, until it gets enough heat, will melt entirely. But note that, this is what I want you guys to understand here. We're still gaining heat here, but notice our temperature isn't going up. So the sensible question would be, where is that heat? Where's that energy going? And the energy is going into separating the particles further from each other. That's why you start out as a complete solid, and then when you gain enough heat, it's a complete liquid. And then from there, it starts to change in temperature again, to heat up again, until it gets to that point of boiling. Well, when it's done boiling, you have a whole bunch of steam. Imagine that you could contain this steam. You'd have a whole bunch of that, and you'd still have your heat source. You'd be heating that vapor up into a steam, which is a high temperature gas. So very important to understand the latent heats. All right, no temperature change going on. All right, particles are just they're gaining that energy, but they're using it to spread apart, get further from each other. Molar enthalpy of fusion is our delta H of fusion. You're going to find that we use delta H for quite a few different things. All right, fusion it's also called the heat of fusion. I will refer to molar enthalpy of fusion also as the heat of fusion, and it's the energy required to melt 1 mole of a solid to a liquid with no temperature change. All right, so again, we got our quantitative amount there, our 1 mole, and it's melting. Don't get that confused in your head. I always did for years, because it's the molar enthalpy of fusion. I'm thinking things are fusing, coming together, all right, like in nuclear fusion. But in this case, what we're talking about is the melting of a solid to a liquid. And during that time, there is no temperature change. Again, our latent heat. We express it, like I said, in the universal units of kilojoule per mole. So a lot of times you'll see it in charts as kilojoule per mole. Again, that's for comparison reasons among scientists. All right, same amount of energy is released when 1 mole of liquid freezes. All right, so going in the opposite direction. Now we're not melting, but we're freezing. Now, notice that it said is released. So when we have our ice cube there, and it's gaining that energy, it's endothermic, it's got a positive sign. All right, but when we're going the other direction, when we're going from freezing, what's happening in that case is that the energy is given off. You ever think about it? That's why your freezer has a pump in it, because it's pumping out the heat. All right, because if it can get rid of that heat, then it's going to be cold, so to speak. All right, so it's the same magnitude. So let's say it's 100 kilojoules per mole to melt an ice cube. It's the same magnitude to freeze it. However, it would have a different sign. So it'd be minus 100 kilojoules if we were freezing it. All right, here's another term, molar enthalpy of vaporization, also called heat of vaporization. That's usually what I call it. The quantity of energy required to convert 1 mole of a liquid at its boiling point to its vapor at the same temperature. All right, specific heat. So that's our C value and MCAT of a substance is the amount of thermal energy required to raise the temperature of 1 gram of the substance by 1 degree Celsius. I used water previously. It's of the substance itself. This is specific heat. Usually it's written as C and then a sub SP for specific heat, so you know. Again, that's a universal terminology, so we all know what we're talking about and how much we're talking about. All right, and the units for that is joule per gram Kelvin. All right, so here's our thermal energy input. Q is equal to MCAT. You guys know it. Q is the thermal energy put into the system. M is our mass, our specific heat, and our change in temperature. I'm not going to spend a whole lot on that because you guys know it. Just as the rate of heating is related to specific heat, so also is the rate of cooling. Like I said, it's the same magnitude, just a different sign. So the operations, okay, melting, freezing, vaporization, condensation, they would have the same magnitude, whatever that's calculated to be, but a different sign, depending on the direction that it's going. All right, substances with higher specific heat values retain heat for longer periods than those with low specific heats. Okay. Again, this is a point where I'll ask the students about specific heat. What would you rather me throw at you? I just took out of the oven an iron, let's say 400 degrees Celsius oven, an iron bar, and also some aluminum foil. And I asked them, which one would you rather me throw at you? The aluminum foil or the iron bar? And again, most people, except some of the yahoos, will say the aluminum foil. And then I ask them why. Why would they want that? And they said because it won't be as hot. And they're right, because aluminum doesn't hold on to heat as well as iron. Same thing's true with water. Water is 4.18, 1 calorie. That's a high specific heat. Water holds on to its heat very, very much. And you know this. Think about during the fall time. All right. You go into a Cubs game. It is a Cubs game and not a White Sox game. And you usually can go in the fall without a coat. All right. Why? Because, well, the stadium's close to Lake Michigan. Lake Michigan's a huge body of water. It's just coming off the summer, being heated all summer. It holds on to that heat quite well. So any wind blowing into Wrigley Field there is warmer. Whereas now in the springtime, if we had baseball, you would most likely wear a coat because we're coming off of the freeze, the winter, and it's been very cold. It doesn't, Lake Michigan doesn't freeze except maybe the near the beaches, but it is definitely lost some of its heat. All right, so the wind blowing into Wrigley Field in that case would be cooler. Hence, you'd want to wear a jacket to the ball game. All right, so here again is the heating curve. All right, they're showing you the different areas of it. This is the molar enthalpy of fusion for water. All right, it's ice turning into water. So again, like I had previously said, right here is where it's starting to melt. Here it's fully melted. Right? Point 2, we're changing in our temperatures here. You can see that. All right, we're moving up and we're changing in our temperature there. And unlike where we have our latent heats here, or our molar enthalpy of fusion, heat of fusion, where we have no temperature change. It's staying right there at 0. All right, now this is again what they call the sensible heat. Kinetic energy is increasing in this case. Specific heat of water, very high. All right, now at 3, we're starting to boil. So we start to boil right here. All right, and it's going into water vapor. And finally we get all, think about it, if you did your macaroni and cheese and you put a pot of water on the stove and then you went outside to play some baseball and you forgot all about it. Well, you'd come in, there wouldn't be any more water left, all right? It'll be all vapor. And since it has so much area, it has area to spread out. So it wouldn't be heating it much either. All right. So this right here, this straight line is what they're calling the heat of vaporization, or the molar enthalpy of vaporization, when it's going from water to steam itself. Steam would be right up here. When we start to heat, our temperature's changing again. We're starting to heat the water vapor. Enthalpy of reaction. All right, that's what I was talking about before. It is our products minus reactants. All right, so you'd find the enthalpy for your products minus the reactants. All right, and you can see that this case we have a negative enthalpy. And what they're showing, when you show heat, depends on which side of the reaction it's on. All right, in this case, you can see that it's on the reactant side. Excuse me, on the product side. And if it's on the product side, you know that heat's given off. Whereas if we have it over here on the reactant side, heat, we know that it's gaining that heat. It'd be endothermic reaction as opposed to an exothermic reaction. That's why they put that minus there, to show that it is an exothermic reaction. All right, this is simply called a thermochemical equation, and it's like a chemical equation, but they call it thermo because it's got the heat involved. All right, the products in an exothermic reaction have a lower enthalpy than the reactants because energy is released during the reaction. I hope that's pretty clear. The products in an endothermic reaction have a higher enthalpy than the reactants because energy has been absorbed. All right, enthalpy heat of formation. It takes place at standard state. Again, so this is so we can get it standardized. So it's at a standard state of 25 degrees Celsius and 1 atmosphere. Standard molar enthalpy of formation, which is our delta H of F, is the enthalpy change for the reaction that produces 1 mole of a compound in its standard state from its elements in their standard states. And this is when we start to talk about what's known as Hess's law. So know again that this is, they got big, huge charts of the enthalpy, the heat of formations, and you can see them in the back of the chemistry books, and that's what they use when they're looking at reactions. And they must be in their standard state, just like STP at standard temperature and pressure for gases was 0 degrees, 1 atmosphere. In standard state, when we're talking about the heat of formation, is 25 degrees Celsius, 1 atmosphere. And most values of heat of formation, enthalpy of formation, are negative, which means what? Yes, heat's given off. All right, you think about it around you, most things are exothermic. Enthalpy, heat of combustion. All right, we're talking about complete combustion here, so that involves complete reaction with the oxygen. All right, incomplete combustion is not good, especially if it's going on in your furnace downstairs. And that's what's led to, unfortunately, some deaths in people's home is incomplete combustion in the furnace, where it's producing not the CO2 and water that a normal combustion reaction will produce, but it's producing carbon monoxide, carbon dioxide, CO2, and water. And carbon monoxide is a deadly gas that can silently kill, because you cannot smell it and you don't know that it's invading you. All right, standard molar enthalpy of combustion, our delta H. Now this is, all right, that degree looking sign there, that's just telling us it's in standard state. So when you come across that, you know that you have to be in standard state. All right, so our standard state, our standard molar enthalpy of combustion is the energy released as heat by the complete burning of 1 mole of a substance at standard conditions. Standard condition again is 25 degrees Celsius and 1 atmosphere. All right, let me get that out of your way. All values of our enthalpy heat of combustion are negative because these reactions are exothermic. I think you would agree with that. All right, think of your car, gasoline. What's going on? There's little fires that are being blown up in the pistons, and that is what allows the piston to move up and down, and that's connected to a bunch of other mechanical pieces that end up moving your car wheels. And at the same time, the exhaust that's coming out of there is our carbon dioxide and water vapor. And you can see if it's an old system, there'll be water, actual liquid water dripping out of the tailpipe there. There, you know, you got some incomplete combustion going on in the engine. You want to get that checked out. All right, so how do we calculate this? Two-chemical process. Each reactant breaks down to its elements in their standard states, and the elements are in their standard states recombine to form the products. All right, so bonds. All right, in order to break a bond, it requires energy. When bonds form, energy is released. That's why nitrogen, think about it. Nitrogen has triple bonds. Nitrogen's used in many different explosives, including TNT. And you can see that what happens is when nitrogen, it would take a tremendous amount of energy to break that triple bond, all right? But then when it does form, a tremendous amount of energy is given off. All right, here's an example. So we have our delta H of reaction is a negative 65.7 joules. So we know that the energy is being given off in this equation, this chemical equation. Let's take a look at the molecular level, what's actually going on here. All right, you got your PB and your O, which is the solid there. All right, coming into contact with our carbon monoxide, which is the gas there. All right, you can see that 217.3 kilojoules is required to separate the two. And then you have your lead in its standard state, so it had 0 kilojoules right there. Oxygen also 0, since that is how it usually is. It's O2 and Pb. All right. Whereas in this case, you have your CO of 110.5 kilojoules. All right. In order to separate them, that's going to cost quite a bit of energy. All right. And then when they form, it gives negative 393.5 kilojoules. All right, so then what we'd want to do is we'd want to take the sum of our reactants. So the sum of these, and you can see that that's about 327.8. All right, so these are our reactants. I just adding them up. I got 327.8 kilojoules. And I'll add these, our products up. You can see that we get negative 393.5 kilojoules. All right, so remember our delta H of reaction was our delta, or was our H, excuse me, of products minus our H of reactants. So it's the negative 393.5 minus the 327.8 kilojoules, which comes out to be the negative 65.7 joules. Should be kilojoules. Yeah. All right. Error there. This reaction is exothermic. Hopefully no big surprise there. All right, so Hess's law, what's that tell us? That's the enthalpy change of a reaction equals the sum of the enthalpy changes for each step of the process. So the enthalpy of the products minus the enthalpy of the reactants gives us the enthalpy change of the reaction itself. You can look that up. You'll look up these values in your textbooks, or I'll give them to you on the problems. All right, so another way to write this is our delta H standard, our enthalpy standard reaction is equal to the enthalpy change in the reaction decomposition plus the product formation. So they just switched them around, so it's not products minus reactants in this case. You switch them around, you have your reactants plus your product formation. You'd end up with the same number either way. But this is officially how Hess's law is stated. And again, that's just the sum, as I pointed out in the previous slide. All right, so the two general principles for combining thermochemical equations. Remember, thermochemical, that just is a regular chemical equation that has some heat involved with it. When using Hess's law, you may use any balanced equation. It needs to be balanced, but remember to change the sign of the delta H if you reverse the equation. All right, so if we're take H2 plus O2 and we make H2O, balance it, and this delta H reaction. I should know what it is, but I don't. I'm sorry, I forget. All right, but let's just pretend. Let's say it's minus 100 kilojoules per mole. All right, and if I were going the opposite direction, if I was going from the two waters there and then producing the hydrogen and the oxygen gas, then in that case it would be positive. Okay, so you'll want to remember that. And that you need to multiply the coefficients of the balanced equation. That's why it's important to get it balanced first. To get the desired equation when the coefficients are added together. But remember to also multiply your delta H by the same number. So if you're multiplying through, so let's just take our previous example there. All right, so if I said it was 2H2 plus O2, 2H2O. All right, and I said that was minus 100 kilojoules per mole. All right, if I multiply this through by 2, so let's just pick any number. I'm just picking 2. So then I make it 4H2O plus 2O2 yields 4H2O. Then I have to also multiply our delta H of reaction there, which is negative 200 kilojoules per mole, minus 200 kilojoules. Remember, it's not a negative number in the true math sense that it's less than 0. It's just showing us that heat is given off. All right, I think that's enough for now. Let me know if you have any questions.